Hello everyone. Today we'll be talking about the directing group effect. Okay, so that means we're gonna have an aromatic ring, and we'll have both group, an ortho para director and a meta director on the aromatic ring. But first, let me quickly give an explanation of what does ortho para director mean and what does meta director mean. Okay, so let's say we have an aromatic ring. Okay, I number it. I'm numbering my carbon to make it easier so that we can talk. Let's say you have a group on it. Let's say that's a reference group, right? A group on carbon 1. In terms of position, the carbon that are adjacent to, let's say, on carbon 1 is the alpha carbon because it's holding the reference group. Those carbon here directly connected to carbon 1, this is the ortho position. That's the ortho position. That's another ortho position. Again, if we go a little further, like carbon 3 and carbon 5, let's say you see how carbon 3 is separate. There's one carbon that is separating carbon 3 from the alpha carbon, right? So this is the meta position. I like to talk about it like meta, middle. It's not really in the middle, but let's say there's a carbon in the middle, right? Separating it from the alpha carbon, right? So this one too, it's also at the carbon 5 is also at the meta position. And the other carbon that is exactly on the other side, let's put this in orange, right? Carbon 4, this is the para position, okay? So whenever you're gonna hear me talk about at the ortho position, you know that those that the carbon that are connected to the alpha carbon, meta and para position. Okay. Let me renumber my carbon. We have carbon 1, 2, 3, 4, 4, 5, and 6. Okay, what we need to know now is that there's groups that will place certain element, right? Either at the ortho position or at the meta position or at the para. What do I mean by that? Okay, let's say if we have, let's take any example, right? Let me say if we have OCH3 at position 1, let's say before we had an empty ring, right? And then we added an OCH3 on it. What this is telling us is that if we want to follow it, let's say this group OCH3 is gonna have an effect on the ring, okay? Because it's either it's gonna withdraw electron from the ring or it's gonna donate electron. The way we can know whether OCH3 is an electron donating group or electron withdrawing group, guys, again, I'm gonna show you the shortcut soon, but let's talk about it, right? Look at this. There's an oxygen here, right? That is full of pair of electron, right? Exactly adjacent to the ring. We know that if there's one resonance we can do, let me put the resonance here. We can know that the oxygen can donate electron, right? Let's say we can do this as resonance, right? I put the 6 inside. Oh, no, it's fine. Yeah, let's copy and paste this. Copy. Let's do this. We know one resonance can be this. Let me move the same. Can have this, and then you put the charge. Right? That's one resonance. Okay. And then we can also do this. And this. At another point in time, we know that we can also do this. Right? Let me copy the second one. Again, I'm just showing you all the resonance we can have in a molecule. I hope this is making sense. Here we can have this, and our charge would be on carbon 4. You see how we're donating electron? And again, at another point in time, we can do this. Okay. All right. So now, let me make sure that we have the charge on carbon 2 and we have the double bond here. So here are all our resonance structure, right? What does that mean? That means we know that resonance, like the resonance, the true structure of a molecule is the average of all the resonance, right? So that means I know that this one, at some point in time, carbon 6 can have a partial negative charge, carbon 4 can have a partial negative charge, and carbon 2 can have a partial negative charge, which means that this OCH3 is an electron donating group, okay? And if we have anything partially positive in the molecule, in the solution, we know that negative attract positive. The carbon 2 will act like a nucleophile, and we will have our electrophile at the ortho position here. Let me copy this again. Okay, we can have it either at position 2, because we can see that carbon 2 has a partial negative charge, or we can have it at position 4 here. Oh, yeah. Carbon 4. Let me put it on top of it, right? Let me remove the negative charge. I think we get it. The electrophile here. Or we can get it at position 6, but it's the same thing as this molecule, right? Whether let me draw it. Let me draw it for you. You can put it here. But these two are equal, right? Because we can see here we would have a nice symmetry. That would be the same compound if you rotate it, right? It would be the same thing. So these are same. So I would even draw this one, right? I would ignore this one. As a matter of fact, let me remove it. I would ignore this one, right? Okay, so these are our two possibilities. In the case of the meta director, electron withdrawing group are meta director. Why? Let's talk about it, right? In this case, we have a CO double bond that is exactly adjacent to the ring. If we draw let's draw the resonance again, right? We know that the resonance will do this, right? It will withdraw an electron. At some point in time, we will have this resonance structure. Let me copy it. Okay, we know oxygen has a positive negative charge for electron, and this carbon here will be positive. Let me again, 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. Right? But we don't care about this one, but guess what? We can go for instance, right? We know that at some point in time we can do this. Okay. All right, that's one. So, okay, let me draw it again. Let's copy this to go faster. And look what's happening, guys. Carbon 6, because it's losing electron, it can have a partial positive charge. The resonance can be this one. In this case, we'll put one here, we'll move that one. Carbon 4 will have a partial positive charge. And finally, we can also do this, right? It's one of those things. It's nice to try yourself, right? So that you can get a good feel of drawing resonance and even understanding the pattern, okay? Here, we have this one here, that one here, and carbon 2 has a partial positive charge, right? Now, what does this one is telling us, right? What it's telling us is that at the ortho position, at carbon 6, carbon 4, and carbon 2, right? They are partially positive. That means the wheel structure on carbon 6, we're gonna have a partial positive charge, carbon 4, a partial positive charge, and carbon 2, a partial positive charge, which means if we have an electrophile or something with a partial positive charge in the solution, right? We know that it's not gonna add to either carbon 6, carbon 2, or carbon 4. Like because we know that positive charge repel each other, so he has no choice. It's gonna have to add either on carbon 3 or carbon 5. So that means the only possible solution product we're gonna get is the electrophile being added at the meta position. So this CO double bond is a meta, it's an electron withdrawing group, which is a meta director. Okay. beta director, so it add any group at the meta position. Okay. And that's all I have for this series for now. And if you want to see the application, well, we're actually gonna solve problem with a ring having both group, electron donating group and electron withdrawing group. Please watch the second part of the video because I didn't want to make this too long. So I figured that cutting it into two can give viewers more option, right? Okay, so see you in the next part for the application of this explanation. See you.